Having seen how differential equations might arise, let's take a look at the simplest interesting differential equation, which is simply the derivative of some function y is proportional to or is equal to a constant times the function y itself. And we'll see this arise in various scenarios as we go through the course, or equations that are very closely linked to this. And now our goal here is to find solutions and talk about solutions to a differential equation, which we'll shorten to DEs. So if someone were to put this equation in front of us and also tell us that k was equal to 1, then we'd simply have the equation dy dt equals y. And if we're going to ask what is y equal to, well, it's equal to dy dt, so that's not very interesting. So we have to be a little more precise and say as a function of time alone. So can we express y with some values here with t involved directly? And it's not obvious yet. We'll see techniques for finding this more generally. But what we can do is use our intuition and say what y is equal to its own derivative. That's what we have here. Y is equal to its own derivative with respect to time. And if you think back to all the functions, polynomials, trig, exponentials. If we have y equals e to the t, then dy dt, we take a derivative here with respect to time. That's going to give us e to the t as well. So for that particular solution, dy dt is equal to y for y equals e to the t. And then we have our y as a function of time as our solution. So this would be a solution here. So that's actually quite nice that we've actually found one solution to this differential equation, more by insight into derivatives and our experience with those than by a standard technique. But it's a good start for working with differential equations. Now we're going to proceed to ask some more advanced questions about this system. For what values of k would we have solutions to this? Last time we just looked at k equals 1, but what if we had a 2 there or a 3? Let's do an example there. If we had dy dt equals, say, 5y, then we'd be asking the same question, what y has dy dt equal to 5 times the original y? Well, again, if we could look back at it for inspiration to our exponentials, if we had y equals not e to the t, that wouldn't work because I wouldn't get a 5. But if we slide a 5 into the exponent here, then dy dt would equal, well, how do we do this? We take the derivative with respect to time, and we'd have the derivative of an exponential is the same exponential, but then we have the chain rule that says we differentiate the exponent, and lo and behold, we have 5e to the 5t, and that's 5 times this part here is exactly equal to what we called y in the first place. So in this case here, if we put a 5 as our multiplier, we would still get a solution, perfectly reasonable, but it would be a little different than our simpler one. It would have the 5 in the exponent. And in general, there's no reason why this wouldn't work for any constant we put out front. So long as we put the same constant in the exponent, we would satisfy the equation. And so our answer would be y equals e to the kt is a solution to, or it satisfies, dy dt equals ky. And notice that this relationship is not obvious. We have to do some intellectual labor here to go from what looks like a fairly simple equation to something that involves an exponential that is not given in the original problem. So that's going to be another common theme. The solutions will not look like the starting equations. Keep that in mind as you go through the course. Now, we found a few solutions. For example, we just said that if y is equal to e to the kt, e to the kt is a function that would satisfy this equation. But is it the only one? It turns out it's not. We can actually generalize this a little bit further and say, what if y was equal to, let's say 10. Let's put a number in here, e to the kt. Well, what we would do is we could take a derivative and see if this still satisfies the original equation. And we would get dy dt is equal to 10. The derivative of this would be 10 e to the kt times k from the chain rule. And we can rewrite that as k times 10 e to the kt. And what we have here again is our original y value. So we do actually have dy dt is equal to ky, verified. So if we put a multiplier in front of our solution, it turns out the multiplier will show up both in the original and the derivative, and so it still satisfies the original equation. So we can actually make this more general and generalize our solution here. And get a solution that is y equals, well, a 10 didn't matter, it could have been 5, it could have been pi, some constant times e to the kt would also be a solution for any value of c that's a real number. Well, in that case, the question about how many functions satisfy this, there's actually an infinite number. They belong to a family, they all have some similarities to each other, but there actually are an infinite number of functions that would satisfy this differential equation if that's all we were provided with. By choosing different values of c, we would get different solutions. Now, what we can do is narrow things down a little bit further by adding what are called initial conditions. So there's lots and lots of solutions in general that would satisfy this equation, but what if we try to narrow this down? And let's do that by drawing a quick graph of t versus y. Those are the functions we're looking for. Y is a function of t. And if we're told that the initial value, or the value at time 0, is 0, then we know that the general form, or we found the general form before, was that y would equal some constant e to the kt. And we ask ourselves, well, how could we go through that point at 0, 0? What we can do is sub that in. This translates to a point where y is equal to 0 when t is equal to 0. We can plug that into our equation. The y is 0 will equal some constant e to the 0. The k gets wiped out by that. And, well, that just gives us that 0 is equal to, this of course is just 1. So we get c equals 0, or a solution would simply be y equals 0. Now what does that look like? Well, that looks like the straight line that just follows the axis there. That would be our solution going through that initial condition. It's not very exciting, but it's certainly a valid solution. And if we check, if y is 0, then dy dt is equal to 0. So let's just confirm that. If y is 0, we'd have dy dt is equal to 0. And if we think of that as slopes, the slope is always horizontal. The slope is always horizontal, and if that's the case, well, we're going to get a straight, flat line for the solution to this equation. So we can use our information about the infinite number of solutions and narrow them down by providing some initial conditions, sometimes to a fairly simple solution like this one here. They're not always so simple though. If we did exactly the same thing, started with our solution c e to the kt as being our y values, or our y functions, then what we can do is plug in t equals 1, y equals 1, and see where that gets us. Now this time it does matter that there's a k in here, but what this lets us do is solve for the constant c out front. K would be given, c is the value we would not know, and so we're going to solve for c, and that'll give us 1 equals c e to the k, bring the k down, we'd have c equals e to the negative k, or if you like it, 1 over e to the k, which is equivalent. What does that look like in terms of a graph? Again, the graph would be the function y over time, we've just been told that the function goes through the point 1, 1. And we have our constant value here, but that's not our solution. So we have to go back and sub this back into our solution and then use that to draw a graph. We'd have y equals, let's write it as 1 over e to the k times e to the kt. And this is constant. And if you think back to how functions transform, this is a vertical scaling. The key thing here is this is an exponential function. And let's assume, just for the sake of graphing here, for k positive, just to get a graph, what we would have there is exponential growth. We would have the point that we're going through here, and otherwise the function would look like an exponential growth function. We know that those tail off towards the axis as x gets smaller and smaller, or t rather gets smaller and smaller. And this would look like the graph of 1 over e to the k times e to the kt. That's where our variable t shows up in the formula. And so what we see is by choosing different initial conditions, but the same equation, we can get interesting graphs, such as exponential growth here, but we can also get simple graphs for some initial conditions. If we started at height 0, at time 0, we simply get the horizontal line, y equals 0. And that exploration of what do solutions look like and what would they mean in a modeling application is again going to be one of the themes of the course.